Okay, so I am working at Symbolic, which is located in close to Paris. So basically, here is my lab. So I don't come from security, I come from formal methods and certification. So basically in my lab, originally we are interested in designing methods and tools to help design very, very safe safety critical systems. So we had a few success stories, notable like Airbus. Typically, if you take the last Airbus planes, they have been designed, all the control command part has been totally verified with many different tools, including our own pharmacy platform. And we have also success stories in nuclear and in railroad and stuff like that. So this is where we are coming from, and we are trying to push up our techniques into cybersecurity as well. So typically, the pharmacy tool has been used to verify Polar SSL, which is a SSL-like library. The verification has been done just before the Heartbleed attacks arrive. Okay, and basically this version was safe and hasn't any bug. So this is where we are coming, and now we are trying to go to security. Okay. So what's the talk about in a nutshell? So the challenge I consider is code deobfuscation, or more especially trying to get automatic techniques to help the reverser to perform code deobfuscation. Standard tools like dynamic and statics are not enough. And my point is that semantic methods coming from originally designed for safety critical systems, but can be adapted and can help for code deobfuscation, but they need to be carefully adapted. One very point is that these methods are working on semantics, meaning the behavior of a program, not the way it is written, and obfuscation preserves semantics. So in some way, these methods are working on something which is invariant by obfuscation. So the talk will try to show how these symbolic methods can help, as well as their limits. Basically, they can help to explore and discover new parts of obfuscated code, to prove infeasibility of some part of the codes, or to simplify part of the code. So this is joint work with many people, including ex-PhD student Robin David and new PhD student Jonathan Salwan, who is also at Quarks Lab and who is developing the Triton tool. So basically the outline of the talk. So first a bit of context on code protection and semantic analysis, then a tour on our symbolic deobfuscation and especially the techniques we are using, which is symbolic execution, including some examples and case study, and then conclusion. Okay, so what's the context? So originally people were looking at man-in-the-middle attack. So basically this is a scenario where the attacker is on the network and computers are safe, and he can only observe message and forge message, and there are lots of non-crypto solutions for that. So basically you can say, okay, here is my cryptographic solution. I can tell you the solution because I know that even if you know it, I have mathematical guarantees that you cannot attack me easily. Assuming the protocol is well implemented, of course. Okay, but here with obfuscation and deobfuscation, we are looking into another scenario, which is made at the end. So now the attacker is not on the network, the attacker is on the computer. So basically the attacker is running your software and you want to take advantage of it. So he can run it, he can rewrite it, he can execute it step by step and patch it on the fly and so on. So in this case, we don't have this nice mathematically proven guarantee. So we are more on other techniques. So typically, why do we want to do that? Okay. So since code is just data, you can execute it, okay, legitimately. But you can also, if you want, read it. So it can be used to steal crypto keys, for example. Or you can also modify it, for example, to bypass security check. So this is not that. This is code and data attack. And you need a protection against that, and this is obfuscation. So just a few, okay, so everybody know here, I guess, but if you are on unprotected code and managed code created by standard compiler and so on, so reverse is not that hard in that case. So what is obfuscation? Just a reminder. So basically the idea is that you have some program which is not very hard to understand. And then with obfuscation, you want to turn this program P into some program P prime, which do the same, morally, behaves like the original program. It is roughly as efficient, okay, but it is very hard to understand. You want to transform your original program into some big block, big piece of code, very hard to understand. So basically, you want to protect your code, your PI, and stuff like that. So this is the goal of obfuscation. So since there is not yet mathematical proven solution, especially there seems to have some solution, but the problem is in the efficiency of the current theoretical solution. So people are usually relying on more ad hoc solution. So typically, if you take this book, you have many, many different kinds of obfuscation and so on. There are commercial tools, there are open source tools. But remember, we don't have any mathematical proven guarantee. So it's not always clear what the strength of this technique is. So a few examples. This kind of obfuscation, what do we have? We have self-modification, encryption, virtualization, and so on. I will just describe a few ones because after I will have some case study on them. So if you consider opaque predicate, what is opaque predicate? Basically, you insert branch in your code, but this branch, you know that they will always be true or always be false. So for example, you can do it with arithmetics. So typically, this arithmetic expression is always true. Okay. And how do you use this opaque predicate? Basically, you put your opaque predicate somewhere. You know that one branch will never be taken. Then you put some arbitrary code into that branch. So basically, the dead branch will point to spurious code. And hopefully, the reverser will waste its time into trying to analyze the spurious code. Okay, this is one technique. You can also have, for example, stack tampering. So here you will play that usually people tend to think that a return instruction go back to its natural color. Okay, but you can trick the program because in assembly there is no formal stack, so return is just some jump somewhere. So for example, here you have a call, then you modify the top of the stack and you return, which is just a jump, so you don't go back here, but you go somewhere else. So in that case, the return site is a spurious code, it is jump code, okay? So maybe the reverser will waste its effort on it. And you hide the real target of the jump. So maybe the disassembly tool will not find the real target. So with obfuscation, you can both add some spurious code and try to hide some legitimate code. Okay. Third example, virtualization. So it's a bit different. So in that case, the thing is, you don't ship your program P. You turn P into you design some bytecode, your proprietary bytecode, your own bytecode. And you have some virtual machine for this bytecode, homemade virtual machine. And now you don't ship your original program, but you compile it into your bytecode. And what you ship is your virtual machine plus as data this bytecode representing the program. Then at runtime, the virtual machine executes your bytecode and then it simulates this program. But the thing is now, if you try, for example, static disassembly, you don't get the structure of the original program, you get the structure of your virtual machine. And the structure of a virtual machine is always the same. Basically, you check the instruction, you decode it, you branch to the good opcode handler, and so on. So here you trade code for data. And so the goal must be to be able to recover the original code. Okay, so this is 3 examples of different obfuscation you can find. So naturally, the obfuscation is the opposite. You start from the protected code and you want to go back to the original code. Okay, that would be perfect. Or maybe you want to go back close enough to the original code. Or maybe you want the obfuscation to help you understand some aspect of the original code. So this is not really well defined here. You have a broad range of possibilities. It's not the same thing if you want only to steal one crypto key or if you want to really go back to the original code. But this is all put into the obfuscation. And obviously into the obfuscation, you can have very small steps, like getting the control flow graph and the instruction back. But you can also want, ideally, you would like to understand the behavior of the program and stuff like that. In this talk, we'll focus only on recovering basic step like a control flow graph or instruction. Okay, so why do we want to work on deobfuscation in an ethical manner? Basically, there are two scenarios. The first one is to assess the power of existing software code protection, because since you don't have any mathematical guarantee, the only way you have to ensure that some code protection tool is very good is to try to attack it, actually, and so to try to do the deobfuscation, okay? Another point, if you are working malware analysis, if you consider like APT or very, very sophisticated malware, in some scenario, you have to really understand what the malware is doing. Think of ransomware, think of like the hacking by XTunnel by APT20I of American Democratic Party. In this case, you really want to understand what the malware is doing. But even most of these highly sophisticated malware, they are highly protected, and they are very obfuscated. So here you are in the scenario where the good guy is doing the deobfuscation against some obfuscated malware. And here the good guy is trying to check if to do the deobfuscation to check if the original obfuscation is strong enough to protect assets. These are our two scenarios. Okay, so this is the goal. Now that we know that we can do deobfuscation in an ethical way, how do we do that? Basically, it strongly relies on human experts. It strikes me when I talk with people from security, with experts. Actually, most of them use quite basic tools with syntactic reasoning or dynamic reasoning, and it always relies a lot on the skills of the expert, and it's quite amazing. But there is a problem, because obfuscation is done automatically. So if you can add very easily lots of obfuscation, mix them in an automatic way, and on the other end you have mostly a human, even if he's strong, at some point he cannot cope. So my point is that we need some better tooling there so that in some way the better tooling you have can reduce this automatic increase in the protection so that the human expert can still cope with the flow. And the thing you would like of such tool is to be able to find hidden parts, since with obfuscation you can hide parts of the code, so you would like to find them. You can add spurious code, so you would like to be able to prove that some part of the code are spurious. And you can also complexify some part of the code so that you don't recognize it just doing some simple operation. So you would like to be able to simplify that. Okay, and obviously, most people here will know it, but if you use standard disassembly tool, it just doesn't work with obfuscation. So if you take IDA, so here normally IDA will just recognize that this is a switch, basically, that you can jump here, 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 and here, and here. Usually it does it, but here we just add this. So this is a jump on EX. And here what we do, we put EAX on ECX and then ECX on EAX, so we put it back, so it doesn't change anything. But if you do that, now IDA is able to recover the instruction, but not the edge. And this is not really obfuscation, this is a very, very simple pattern. So the thing is, since it's very syntactic, it cannot cope with obfuscation, because it bases analysis on something which is heavily modified by obfuscation. Okay, so how do we do that? Remember, I come from formal methods, program verification, and semantic analysis. So I have a very beautiful hammer, and I am looking for a very beautiful nail. And it seems to be a very beautiful nail. So obviously, I will try to attack the problem by lifting techniques developed for safety critical systems to this security setting. The very, very good point, if you think of it, is that these techniques are based on semantics. They really try to understand the meaning of a program, the behavior of the program, what it does. And a very important property of obfuscation is that it doesn't change the behavior. okay, you want to protect your code, but you want it to be still your code in some way, or it's totally useless. So, contrary to syntactic methods, which are working on something which is completely trashed by obfuscation, these techniques work on something which is which remain the same. Another point is that in this technique, usually, you can reason about infinite sets of execution or infinite set of states at a time. So basically, you can find rare events. It's not that hard. For example, if some part of the code can be launched only if it's Christmas, then for testing, you will never find them. In formal methods, you might find them. It can also make proof about infinite sets of execution and so on. But obviously, it's not so easy because it has not been designed for binary level analysis. It has not been designed for obfuscated code and so on. So I don't claim it is magic. I just claim maybe these are good properties which could be useful. And so in the rest, I will, and also these techniques are based on, comes with strong theoretical ground and mathematical guarantee, so it's interesting as well. So I will try the rest to see how these techniques can be adapted to these three goals. Okay. Just a point about formal methods, if you are not really used to it. So basically, you can see that some combination between software engineering and theoretical computer science. The original goal was to really to be able to design software which are totally proved by design to have absolutely no error. It can look like a dream of crazy mathematician, of crazy logician. But actually, it's a clear and very big success now in safety critical industry. So for example, in Airbus, the last Airbus, 380 or 400s, they don't do unit testing anymore. They don't care, they probe them. So if you are in this, if you take this kind of planes, you are in something which works because of formal methods. And so they don't do, they replace all the tests by formal methods proof. They also check all performance like worst case execution time and stack usage, memory consumption by formal methods. And there are also some certified compiler to ensure that the analysis they do on the source code is still valid on the binary code. But this is for safety critical system again. Another point is that the French research community is very, very good. There is at that. There is currently a very big shift in the US to put formal methods everywhere to create some secure stack, secure OS, secure. And all the tools they are using, most of them come from France, like the Coq Interactive Browser, the Camel Language, the Pharmacy Analyzer, and so on. Okay. So we have this good idea using formal methods. Okay, but which one? Here comes the problem. You have many of them and many variants, and it's a bit complicated. But here we have a constraints. We would like something which is not too hard to adapt to binary level. And we would like something which is quite robust to nasty low-level tricks. Typically, if we encounter self-modification, we don't just want to stop and say, oh, I don't know. Okay, so the good thing now is that basically, okay. Yeah, this is the PDF version, not the PowerPoint. So now, actually, in all of that, you have only these techniques which satisfy this constraint, I think. So we will be based on symbolic execution. So what is symbolic execution? So the idea basically is that to realize that, okay, proving a program in an automatic way is very complicated. But if you don't want to prove the program, let's say you just want to explore it. If you have a program and you would like to reach failure, then you take a path in your control flow graph which arrives to failure. Now it's very, very easy from that path to create what we call a path predicate, which is a formula over the input. So here are the input, value for x and for y. And this formula really represents the condition on the input so that if you satisfy them, you just follow the path. So I will check just after we create. So then, if we have a solution, we know that we follow the path. So here we reach failure. Then we take this formula and we send it to an automatic solver. There are lots of guys in the academia who are doing automatic solver. These automatic solvers are now very, very good. for example, SMT solvers or SAT solvers. And so you don't care of this part. We just have to create the formula and send it to the solver and get the solution back. If we get the solution, it's an input, and we know it will reach failure. And if there is no solution, then there is no solution. That's it. So how do we compute that? Usually it's quite easy. What you have to update, you follow your path, and instead of doing the concrete computation, you update some constraints of the path and some binding between your current variable and some new logical variable. So at first, x, y, and z are binded to variable x0, z0, y0, and z0, logical variables. Then if you do that, now z has changed. Now the content of z is equal to 2 times the content of y at this point, and y at this point is the logical variable y0, which has been done here. Okay, now you add some new constraints. So you take the logical value of z, the logical value of x, and now they must be equal. And then you have another constraint, and so on. And if you had some assignment, you would update that, and so on. So it's quite easy. You just follow the flow. And then you can get everything. So obviously, you have some difficulties here and there, but this is the rough idea. So the good point is you don't have any false positive. If your technique tells you this is an input to reach this point by following this path, if you don't have any bug in your implementation, then it reaches the point. It is robust. I don't show it here, but you can mix it with dynamic analysis. So if there is some self-modification, encryption, stuff like that, you can always say, okay, I stop to reason symbolically, I just execute. So you have some trade-off. And it extends rather well to binary code. You need to work a little bit, but other formal methods are just powerful to adapt to binary codes. Okay, so for example, what can we do with that? This is the architecture in our prototype, which is called BinSec. So basically, we start some architectures. You encode them, you encode your program to some intermediate representation with very few constructions so that it's easier to work with. And then you have this symbolic execution. We have also a bit of static analysis, but it's harder. And then we have dedicated analysis to malware or vulnerability. And we rely mostly on variants of symbolic execution that we present after. BinSec is not the only tool of this kind. You have several of them. So typically you have Triton, which follow the same. Usually you always have this step of going to some intermediate representation, then this path predicate computation, path exploration, and so on. Okay, so how does it work in practice? So if we want to explore some code, actually, if you want to explore some code, you just need the standard dynamic symbolic execution algorithm I just showed you. The idea is that you will follow path, and when you find a branch you have never taken before, you try to find an input which follows the path, this branch. If you go onto a jump, you try to find a new target, and so on. So you just explore and try to find new path. The good point is that it will find real path. You cannot get into wrong path that doesn't exist in the code by construction. It can find even a rare path. So if there is only one input on a few billion that can lead to that path, you don't care. As long as the constraint can be solved, you will find it. Finding the path doesn't depend on the sparsity of the number of inputs leading to it. It just depends on is your solver able to find the solution or not. And in some way, you can find it as dynamic analysis on steroid. The good point with dynamic analysis is that it allows to bypass many protections, self-modification, you don't care, you go. Encryption, decryption, you don't care, you go, and so on. But you can miss part of the code. So you have all the good advantage, and in some case, you manage to find more part of the code. So just few small example. Yeah, okay, there is not the animation. So if we take our example back, now suppose we have some path which reach here, then we can create a path predicate. We can ask for a first solution, then we will get some value for the target. So let's say this one. And now we can reuse the same predicate and say, hey, okay, but now I want a solution where the jump is something else. And it will give you another solution. And you can do it again. I want another target. You will get this one, and then it will stop. And on this example, actually, you will find that you can go here, here, and here, but actually you cannot go there and there. So you can find new target, but you can find only legitimate target. If you think of track meet challenge, small track meet challenge, maybe there will be one tonight. So where on small example, simple example, basically you need to find a secret. And if the input you gave is indeed the secret, you go on success, otherwise you go on failure. Basically, you can solve this simple example just by enumerating all the path and finding a path which goes there, solving it, and getting a solution. So this is the kind of thing you can do. Okay, more original now. We want to prove that part of the code are really cannot be reached at all. Okay, you can have this issue in reverse if you think of it. Obviously, is this branch dead or not? My dynamic analysis doesn't pass through it. But, yeah, I am just unlucky, or maybe maybe it's a trick and I cannot go there. On the other hand, when you have some return, maybe it would be nice to be able to prove that the return always go back to the caller. So when we say infeasibility, it's either something which is never true or something which is always true. Because if you know that this return always returns to this caller, then you don't have to care about it. There is no trick here. If you have a dynamic jump, how do you know when you have found all the targets? If you have some expression and dynamically you see that it's strange, but it always evaluates to 15. Does it always evaluate to 15? And so on. And obviously you cannot use symbolic execution or dynamic symbolic execution for that purpose. It gives an approximation. But to really prove, you would need to enumerate all paths, and it's not possible. So we are using backward symbolic execution with a bound. So basically now, let us consider the case of path predicate, so of opaque predicate. So we want to prove that a branch is dead. You cannot pass through it. How do we do that? We start from this condition, and now we go back with a given bound on, let's say, 20 steps, 15 steps. Okay, so we compute some formula which say that basically if any execution wants to reach this predicate with this value, it must first pass through this frontier and then respect this condition. And now if your solver say now that there is no such solution, it means that in some way define a frontier. Then you say that I start from the input, I want to go there with this property, but I know I will never go further than here. And so there is absolutely no execution that can go here and have a good property. Basically, the predecessor in cat step, the set of predecessor in cat step of the property you want is just empty. So with this, you can do proof, actually. And actually, it also a very good property. It scales very well because it depends on the bound you give. It doesn't depend on the size of a trace, and it doesn't depend on the size of a program. Because forward symbolic execution may have difficulties to scale with the number of paths. Okay, a few case studies with that, which were done with Robin David. First one on packers. We took some packers, we packed some programs, and we checked some trace, and we wanted to see. So the packers have all the protections, and we wanted to see if we were able to detect some opaque predicate and some co-stack tampering and stuff like that. And actually, so the technique was able to go on quite big trace, and we were able to find many, many things. So basically, the technique was working from this point of view, and considering that there is on this trace there is also encryption, self-modification, and so on. Another case study of external malware. So if we take it to back, so the kind of malware that has been used to hack the Democratic National Congress. So we came up with two heavily obfuscated samples. Looking at them, we saw that there were many, many opaque predicates, heavy protection, and our goal was to detect and remove this protection automatically. So we wanted to see if we were able to do that. And actually our techniques for opaque predicates was able to identify 50% of the code as spurious in a fully automatic way in less than 3 hours. So when we say that spurious, either it is just junk code, you cannot reach it, or it is just used to compute the opaque predicate itself. So it is just in the protection layer. Okay. So this is the kind of things we have been able to achieve. Okay, now, third part, simplification of the code. So we would like in certain cases, the obfuscation is not used to mask the control flow graph, but to mask the kind of computation which is intended. And we would like to recover this hidden simple expression. You can think of junk code, we would like to remove it, junk computation, which are useless, opaque values, which are always the same value but look strange and stuff like that. And actually, symbolic reasoning is a priori well adapted because you have this formula, this symbolic expression, and very few operators. We could think of use it either normalization or rewriting rules. For example, you have a plus b minus a, and you should be able to compute automatically that it's b. Okay. I take simple case. And you can also have some kind of solver-based proof. For example, you have some complex expression, you have another expression, which is simpler, and you think they are equal, then you just ask to the solver, try to find me a counter example such that the two expressions are not the same. If there is no solution, then they are the same and you get your simplification. This is a rough idea. Okay, so the case study here is about devirtualization. So it has been done by Jonathan Salwan, who is not here today, it seems, on his tool Triton, and it is worked on at Workstar. So the challenge is the following. You have this virtualization step, and what we want to do is to go back to the original program here. We consider not arbitrary program. We consider small hash functions, small programs like typically homemade hash functions. Typically, you will find that in video games industry and so on. And it is the kind of function you want to be protected. Okay, so this is small function, but we really want to go back mostly to the original program. Okay, and especially at the end, we don't want the VM at all. We don't want of it. We don't want to see it. We don't care of the VM. Okay, so how does Jonathan do that? And so there are two steps basically. First of all, how does people do it usually? Usually they will have to try to identify in the code the part of the VM, the virtual program counter, the dispatcher, and so on. They will have to understand the bytecode, in some way to reverse the bytecode, and so on. The beauty of the approach of Jonathan is that you do it, but you totally don't know anything about the bytecode, and you are totally unable to know where the VM is. You just don't care. It's totally VM agnostic. How do you do that? You start with binary code, okay? You have some execution. So you use Triton, which is symbolic execution tool, so you are exploring the path. And the first idea is that on this path, basically you have two things. You have the normal management of the virtual machine, and you have the effect of the virtual machine, which corresponds to the effect of the program. And this is interleaved, normally. But the thing is, let us imagine you have a sequence here, and you have an instruction, and you go to another one. It will correspond to some opcode and another one. But you know that after this one, you have always this one. So here, the virtual PC counter will be put at some value. And it will always, in some way, say, I have only one possibility, which is here. So actually, the thing is that on your trace, what you will observe is that you have an interleaving of the virtual machine management and, let's say, the real program. But with simple simplification, like denting and constant propagation, you can get rid of all the virtual machine aspects. So once here you have some simplification, you get rid of all the virtual machine aspects. You have only the effects of the real program. So at the end of these steps, you have kind of a tree of execution, which is cleaned of the virtual machine. Then the other trick is to go to LLVM intermediate representation, passing through Haribo for technical reasons. Once you are there, we basically send to LLVM a program which looks like a tree, and then you ask to LLVM to simplify it, because Clang LLVM has so many optimization and simplification that at the end, he is able to reconstruct LLVM code, but typically duplicate opcode will be merged, everything will be simplified, and common part will be merged. So doing that, we hope that at the end we get a binary code which is mostly identical to this one without any protection. No virtual machine-based protection. Okay, so how does it work in practice? It works well, very, very well. It was presented by Jonathan at STIC last year, and actually we are working on, we have more results and we plan to present publication soon. So Jonathan considers the Tigres challenge. So Tigres is an open source obfuscator, open access obfuscator. I don't remember if it's open source. So basically when Jonathan tried it, so you had 7 class of challenge. On each challenge you have the same kind of obfuscation, but you have 5 different codes. Okay. It's mostly small codes like hash-like function, exactly your target. We focus only on challenge 0 to 4, because for challenge 5 and 6, there is some self-modification, and Triton was not able to handle it at that time. But except for that, it shouldn't be different. And at the time Jonathan tried the challenge, only challenge 1 has been solved. All other challenges remain open. And basically with these techniques, Jonathan solved all the challenge 0 to 4. The thing is, every time you get very, very close to the original code. So Christian Kolberg with the doing Tigres give us the original code and we could compare. Sometimes even you get some code which is smaller, because you can, typically if your code contains useless instruction, then the technique will remove it. And it was very efficient. On 20 examples out of 25, it takes less than 1 minute, and often less than 10 or 20 seconds. In some examples it was harder. I will present it just now. Okay, so I hope you can see more things. So here are more details. So here are all the, basically in red, it goes quickly and with mostly no memory. So the hardest part is here and here, where basically you have, but it's still mostly 30 minutes with 20 gigabytes of RAM. And here is, let's say, 2 hours with less than 200 gigabytes of RAM. So you can have some SSD hard drive and basically do the job. So it's quite, I think it's very efficient for the service. Fun fact about that, there were some protection about duplicate opcodes. They are merged, we don't care. There was one of the challenge as 2-level VM. Okay, it becomes harder, but we still managed to do it. And actually, now Jonathan has tested the techniques against all virtualization protection of Tigres, and the technique is really VM independent. Actually, it doesn't make any difference which protection is used. Okay, so this is the kind of things you can hope to do with symbolic deobfuscation. So I think that it must really be taken into account by people who are doing the defense, because otherwise you can really have problems. Just a few words about limits and countermeasures. Actually, this topic is quite hot in the academic security conference today. So first, obviously, you have a standard limitation of dynamic symbolic execution. So you have problem if there are too many paths. If your solver cannot solve something, then you have some problem. But the guys from the solver are working on the side. So, and since it is quite a hot topic, you have also lots of anti-symbolic execution techniques which are blooming. We can think of how to solve predicate, path splitting, side channel, based assignments, just attacking all the engineering part of the tool, because there are many, many components, so it's difficult to have all the components very without any bugs. Okay, so this is blooming. A note first, all the protection must be input independent, otherwise all the standard simplification of symbolic execution will remove them. So it's not so easy to break the technique actually. And this is a topic, so the harm race is going on. So on the other hand, there are proposal or people working on proposal to counter this anti-symbolic execution things. So we are really in the cat and mouse game actually. There are probably some basic questions which need to be solved or to be answered in some way, because currently the different technique doesn't care of what the exact goal of the attacker is, or the trade-off between performance penalty and protection. So maybe there are some important work to do here on symbolic deobfuscation. So conclusion and takeaway. I've presented the two advantages of symbolic methods and deobfuscation. Semantic analysis complements well existing approach, so it's more expensive, clearly, but it has also some advantage, so it should be used in combination, and obviously with a reverser himself. In some way, it is well adapted because semantic is invariant by obfuscation. It can help you to explore, prove infeasibility, or simplify, and there are some very promising case studies. I think from this research point of view, the next step are anti-anti, symbolic execution, and so on, and opening the way to fruitful combination, because clearly most papers on symbolic execution focus on a few protection, while getting rid of each protection is clearly not the same thing as getting rid of the combination of protection. And even on the attack, it would be nice to see how all of this can be combined, and possibly with interactive user. And on the last point, formal methods can be useful for binary level security, but you must really adapt them very carefully. Thank you for your attention.
Thank you, Sebastian, for this pedagogical talk. We have time for a few questions. Yes?
I have a maybe stupid question, but what happens if you have predicate that only is true with probability 2 to the minus 128? Then in your case, you could say, well, this path in the graph is not dead, but actually, when you run the program, you don't care. Effectively, it is dead. So can you detect these kind of things like having a probability in the branches?
But that's a very, very interesting point, because remember, obfuscation, you must keep the meaning of a program. But actually, in some cases, maybe not all, but in some cases, it may be interesting to not respect that. I guess if you are protecting a video game, the guy doesn't want his video game, just break. So actually, I think this is a very interesting question on the protection side, protection and attack side. Now, if we do some kind of probabilistic obfuscation, typically, actually, the solver will just tell you there is a solution. He doesn't care. There is a lot of work going on the solver now on trying to have some approximation of the number of the solution. I mean, in an efficient way, without just enumerating them. But it is clearly not mature enough yet. But we can expect progress on that, so it would be very nice in that case to know that, okay, there is one solution, but actually on the space of solution, there is only, I don't know, less than 100 on 1 billion. So is it normal or not? And it's to the reverser, because if you think of, I can trigger this part only if it's Christmas, this is a case, or it's, yeah, you can pass it only once, but you want to explore it, but in the case you mentioned, you don't want to explore it. You can also maybe think of kind of probabilistic analysis, but clearly in null static analysis, probability makes everything much harder in formal methods. Formal methods have been clearly designed for the worst case, not for probabilities at first.
Time for other questions? Remark? Yes?
I was just wondering at the part where you do the backward symbolic execution, how do you detect like jumps or like even dynamic jumps?
Oh, because actually I went quite easily. So we have first a dynamic execution, or forward symbolic execution, like you want. So it gives you some approximation of the control flow graph, and then you do your backward on that. So which means that in that case, the technique has both, it can false negative, so it can miss a back predicate, but this is normal, but you can also have false positive because of control flow graph approximation.
Time for one last question. Okay, so thanks again, Sebastian.
Thank you.